So all of you can see my screen, right? Yes.
Yes. Yes.
Oh, good. Okay. Good morning, good afternoon, everyone. It is a great pleasure and honor to introduce Professor Stefano Galatolo as the speaker of today's ISQGD Distinguished Lecture. Professor Galatolo is a professor of mathematics at the University of Pisa, Italy, and is internationally recognized for his fundamental contributions to dynamical systems, ergodic theory, statistical properties of dynamical systems, quantitative recurrence, dimension theory, and computational aspects of dynamics. His work beautifully bridges rigorous theory with quantitative and computational methods, offering deep insight into the long-term behavior of complex systems. One of Professor Galatolo's major contributions lies in the study of quantitative recurrence, decay of correlations, extreme value theory, and statistical laws for deterministic dynamical systems, including systems with hyperbolic, partially hyperbolic, and non-uniformly hyperbolic behavior. He has also made influential advances in algorithmic and computable aspects of dynamical systems, helping to clarify what can be effectively computed in dynamics and how numerical data relates to rigorous theory. Professor Galatolo has authored numerous highly cited research papers in leading journals and has played an important role in connecting ergodic theory, fractal geometry, dimension theory, and applied dynamics. His work has had a lasting impact on both pure and applied mathematics, and it continues to inspire researchers across multiple disciplines. Beyond his research contributions, Professor Galatolo is widely respected as a mentor, collaborator, and leader in the international mathematical community. We are especially grateful for his long-standing support of interdisciplinary dialogue between dynamical systems, geometry, and quantization-related problems, which aligns beautifully with the mission of ISQGD. We are truly delighted to have Professor Galatolo with us today, and we greatly appreciate his willingness to share his insights with the ISQGD community. The title of his talk is Extreme Events, Local Dimension, and Heating Time Statistics in Deterministic and Random Dynamical Systems. Please join me in warmly welcoming Professor Stefano Galatolo.
Thank you for this very nice introduction. And so I can share now.
Yes.
Okay. So I will share my slides. Okay. Let me check that it works. Yes, it looks like it's working. So thank you. Let me thank the organizer for this invitation to speak. It's really an honor for me to contribute to this distinguished lecture series. And what we would like to talk about today is about the relation between, let's say, the heating time and the fractal dimension of invariant measures, and also other feature of important feature of dynamics, which are like decay of correlation or maybe arithmetical properties, and so on and so on. So let's go to the matter. So I will start trying to connect the idea of extreme event to heating times. Later, time permitting, we will come back to this extreme events theory. But let me just say what it is about. And let us put ourselves in the simplest dynamical situation, which is, let us consider a discrete time dynamical system. So there will be a certain phase space, big X, and a certain map from X to X, which is whose iteration generates a certain dynamics. And let us suppose that there is also an observable with real values. And we choose a certain initial condition. We have a certain initial condition, and then we start the dynamics from this initial condition, and we look at the evolution of the value of the observable that we observe during the dynamics. Well, in this framework, once you choose a certain, let's say, high threshold for the observable, a threshold which is so high that when you overcome this threshold, you think, this is extreme. Now the value of the observable are becoming extreme. Well, the first time where the evolution of the value of the observable overcome the threshold is what is called an extreme event. This is one of the points of view on extreme events. The other equivalent point of view is it's equivalent, but it's like instead of looking at the time, you look on what is the maximum value of the observable that you observe if you give a certain time for the evolution, like after time 1000, what is the best, the highest value, and then you increase the time and you see how the maximum increases. But these are two equivalent points of view. And so this is what is let's say, what extreme event theory is about. And let us see what heating time theory is about. And we will see that is more or less the same thing. In the heating time point of view, you have still a dynamical system, and you have a target set. Usually, B, the target set, is chosen to be like a small set, and you look for the first time that your dynamics, starting from a certain initial condition, enter in the target set B. So you define an heating time of the target and also related to the initial condition. So the heating time of B, starting from x naught, it will be the first time for which you enter in the target set. Of course, these two problems are strictly related because, of course, the extreme event point of view is related to the heating time point of view by taking as target set the set of points in the phase space for which the observable is above the threshold. So, in some sense, the extreme event point of view is a special case of the heating time point of view. And now let's enter in discussing heating times a little bit more in detail and see what kind of statements or properties of the heating time we can prove in dynamical systems, and what kind of assumptions are needed. So the statements that we will look at, will be statements about the probability of the heating time to behave in a certain way. So in some sense, we will not study, you see, the heating time is depending on the target and on the starting point. We will a little bit forget the starting point, because since we are looking for small targets or extreme events, we think that we will need to iterate many times. And usually the initial condition of a dynamical system in real application is known only partially, and if you iterate many times, you lose a lot of the information that you have in the initial condition. So instead of focusing on a certain initial condition that you don't know, you try to estimate the probability of a certain behavior to occur, and that is equivalent to say, well, how big is the set of initial condition that gives you this behavior. So this is why we will look at this kind of probabilistic statements. And of course, once you want to estimate a certain probability, you have to choose the measure that is measuring the size of sets and the probability of events. And usually there are two possibilities. One is that you are going to consider a certain invariant measure for your dynamical system, and this will be the measure that will measure the size of sets. Another possibility is that the phase space maybe is a manifold. There is a natural measure defined on it, for example, the Lebesgue measure or some Riemann measure and so on and so on. And you try to formalize the size of the set according to, for example, the Lebesgue measure. And I think we will see both of these approaches. So, what is the heuristics? Let me express some heuristic principle from which many results can be derived in some sense as a formalization of this heuristic principle. How we can have an idea on how big is the heating time. So this is a small picture of what's happening. There is a small target set, an initial condition, a certain dynamic, and a certain orbit, and we are looking for the first time the orbit enter in the set. A first intuition is that the smaller is the set, the longer is the time that you expect to wait. But smaller in which sense precisely? A first good idea is that maybe your dynamical system has some invariant measure mu, and since we are looking to small targets, and so we need many iterations, and mu will represent initial condition, how possible initial condition will distribute in the space after many iterate. Mu represent this measure represent the density in some sense of how likely is to find a point in a certain spot in the space after many iterates. Since we are likely to wait for many iterates, mu is a good measure to measure how big is a certain target. So, in some sense, if the target is B, mu of B will be probably a good, okay, I deleted too much. Mu of B can be a good way to measure how big is the target. And so suppose that you have a target set whose measure is like this, 1/1000. How many iterate you expect to hit this set? Maybe a good guess will be, okay, if the system is chaotic enough, the orbit will look like random points, but distributed as the invariant measure. So probably the heating time problem is similar to the heating time for independent variables and true random systems. So you expect that if the measure is 1/1000, maybe after 1000 iterate, you are likely to hit the set. So maybe a good guess is that probably if the system is chaotic enough, the heating time of a certain set will behave like the inverse of the invariant measure of the target. And many of the results about heating time theory and also extreme value theory are some kind of formalization of this idea. And in some cases, you formalize the idea, for example, looking at smaller and smaller targets and proving that the way the heating time increases asymptotically will be similar to the way the measure decreases by the inverse, by taking the inverse. So you measure some kind of asymptotical equivalence between these two quantities as the target goes smaller and smaller. Sometimes you prove, and this will be like the logarithm law approach that we will treat in the first part of the seminar. Sometimes you prove something like the expectation of these goes like the inverse of the measure, and then you try to to estimate how the in time is distributed around the average, so you know the probability of deviating from this equality, and this is the distribution of it in time point of view that we will treat in the second part of the seminar if we have time. Uh, uh, so as a first mm, general comments on this heuristic idea is that what we are going to see is that it looks like something like this. Okay, if the system is chaotic enough, we can prove something like this, but this is not always true, and this is maybe a little bit surprising. There are systems which are a little bit chaotic. For example, they are mixing, but they are slowly mixing. And in these systems, the eating time becomes in a way that it is much bigger than the inverse of the measure of the target. Much bigger, like more than the square of the inverse of the measure of the target. So there is not even the same power law behavior. And this is, we will see that this can be caused by some particular arithmetical properties that we consider that we can have in the system. So let's go on proving the first formalization of the general idea. So the general idea, I recall, is like the time will be like 1 over the measure of the target. And we try to formalize this like in the asymptotical sense. And so in order to do this, we try to extract from the behavior of the time some indicator for his asymptotics. For example, the scaling rate of the time with respect to the radius. So you could, for example, plot like in many applied scientists they do, they plot the time versus the radius in a log-log scale, and then they take the slope of the graph. And if you do like this, you are considering a limit like this. And this can be a kind of indicator for the power law behavior of target set of dating time of small target set with respect to the radius. Sorry, I forgot to say that again, we put ourselves in the simplest meaningful case. So we consider as target sets some ball centered at certain fixed point, not fixed in the sense of dynamics. I mean, you consider you fix a certain point y, which will be the common center of all the targets, and then you consider balls, shrinking balls as targets. Then you can consider the limit of the logarithm of the time that you need to eat these small balls divided by minus the logarithm of the radius. And of course, you can consider lim sup, the lim-inf. And if these two limits coincide, you have a certain indicator. And if you have a certain indicator, it means that the time scales as r to the minus the indicator. So this indicator gives you the exponent of a power law representing the asymptotic behavior of dating time.
Can I
And
interrupt with a
if
quick question?
yes, please.
Yeah. A quick question. Is tau the first hitting time or the averaged first hitting time?
Is the first hitting time. You
First
fix
hitting time.
you fix an initial condition and you wait for the
Excellent.
first time that your initial condition enter in the target.
Understood.
Then you decrease the radius. This time will increase. And then you see how fast it's going to increase the time, and you measure the power law behavior by this indicator. Okay?
Thank you.
So this general principle is valid. It means that the indicator representing the power law behavior of the eating time equals the indicator representing the power law in the behavior of the measure. And since you are interested to fractals, you know that this is important for fractals because this is the local dimension of the measure at the point y. And if you can prove something like this, these are now called logarithm laws. And we will see very soon why. Because we are going to see two old examples of logarithm laws, or statement like this. And the first one that I like to show is the classical theorem by Erdos and Reni about a discrete probability situation in which you toss a coin, and when you toss the coin is you consider independent outcomes with a certain probability, but you can suppose probability is 1/2, classical coin tossing. You look at, okay, you toss the coin n time, and you look at what is the longest run of heads that you have seen until time n. And what they prove is that this longest run of head that you can see, it almost surely increases like the logarithm of the time. This run of head, they increase logarithmically. For example, if 1 is head and 0 is tail, and you toss the coin and you get these outcomes, R of 2 is the longest that you have seen after 2 coin tossings. So it's 1. This is the only run of it. But after 10 tossing, you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see that the longest run is 3, and so on and so on. And they prove that for almost surely this longest run increases like the logarithm of the time. And let me say, this is nowadays a kind of simple like theorem, but evolution of this theorem are still used in data compression theory and in application in which people want to know how much time they have to wait to see a certain string appearing in a very long string. And let us see another result that looks completely different. We now go in a completely different environment. Instead of being in discrete probability, we go into differential geometry. And we consider a certain manifold, which is a quotient of the hyperbolic space by a discrete subgroup of isometries. And we put ourselves in the case that this Y is a non-compact manifold with finite volume and constant negative curvature. And on this constant negative curvature manifold, we consider geodesics, the geodesic flow in this manifold. And then we choose a certain point, P, which will be around somewhere in the manifold. Let's be, could be this point here. You consider a certain typical geodesic. You choose at random another point and a random direction, and from this starting point, you start an evolution which following a geodesics. So the geodesic will go around in this manifold, and you are interested to understand how far the geodesic goes from your point P. And of course, the geodesic, since your manifold is unbounded, the geodesic can go as far as they want. In this case of this drawing, it can go this direction or this direction, and it can go to the infinity in some sense. And well, to understand how fast the geodesics go very far, and so what is the longest distance that you can see after time t. And then Salif proved that this increases again, like the logarithm of the time, there is a proportionality factor in front, which depends on the dimension. These two results looks coming from two completely different worlds, but they are, in some sense, we'll see briefly, heuristically, that they are examples of the same principle that we are trying to formalize, that the heating time goes like the inverse of the measure of the time. Indeed, for example, let us look to the coin tossing problem. If you toss the coin and you want to observe a long run of heads, so you want to see many ones. So the first thing is that you can see this process of coin tossing as a dynamical system, and a dynamical system in this case, that is well known, as it is well known, is a Bernoulli shift. And seeing a long run of heads at a certain moment is the same thing as hitting a cylinder in the Bernoulli shift. You consider a cylinder which is starting with many ones, and when you enter there, you will see a string. The symbolic representation of the cylinder will be a string that starts with many one, and then it continues. So seeing a long run of heads is like hitting a cylinder of this form. And what is the measure of how the measure of the cylinders goes as you make the cylinder, the initial prefix longer and longer? It increases, sorry, the measure will decrease exponentially. The measure of the cylinder will the measure of a cylinder like that start like this will decrease like if this is the measure of this, the invariant measure for the Bernoulli shift of a set like this will be like 2 to the minus n. So if the principle that we have stated before hold, it means that the time will go like the inverse of this guy, which is 2 to the n. So the time must increase exponentially fast. So, so if you toss the coin many times, you can expect that in order to hit a certain long sequence of ones, you will need an exponentially increasing time. And so equivalently, taking the inverse, you see that the time that you expect, I mean, the longest run that you can see increases as the logarithm of the time. This is what is formalized and proved rigorously in the Renyi-Erdős theorem. And also in the geodesic case, we are in a similar situation because the measure of the tail of the cusp, this is the cusp. Sorry, my drawing is not very, very good, but if you consider the tail of the cusp like this set from a certain distance L on, it's not so complicated to see that the measure, the Liouville measure of these sets also decreases exponentially fast in L. And so more or less you have the same situation. The situation is that in order to arrive here, you need an exponentially long time. So if you plot, instead of plotting the time as a function of the distance, you plot the distance as a function of the time, you take the inverse, and then you plot the logarithm, okay? So these, we see that these are two statements that looks to be coming from two very different environments, but they are expression of the same general principle. If you look them as a statement about dynamical systems. Again, let me be clear. The dynamical system here are in the first, the coin tossing case is the Bernoulli shift with the classical invariant measure, which is the product measure. And here you have the geodesic flow seen as a dynamical system with some invariant measure, which is well known to be there, which is this Liouville measure, which is more or less like the Lebesgue measure. On the tangent, in the unit tangent bundle. Okay, we have seen two examples. Let us see how general we can prove this kind of asymptotic, power law asymptotic equivalencies. And so let us recall what I've said before. If we want to consider the power law behavior of the measure of small target when you reduce the size of the target, you are led to consider the local dimension of the measure at a certain point. So this is the classical definition of local dimension of a certain measure in point. You have an upper indicator and a lower indicator. And of course, you all probably well know that, for example, if the measure is the Lebesgue measure on a plane, the local dimension is always 2 at every point. What kind of relation between the heating time and the measure can we expect to hold? A first relation is the following one. If you have a measure preserving dynamical system over a separable metric space and you consider a certain invariant measure mu, then for every target point in your system, what you get is that the asymptotic behavior, let's say the power law asymptotic behavior of the heating time, will be always bigger than the local dimension, not always, for almost every initial condition. So the target point is fixed. Then varying the initial condition for almost every initial condition, for mu almost in every initial condition, you get that the scaling rate of the time must be bigger than the scaling rate of the measure, which is the local dimension. And this is true for both the upper and the lower indicator. So this tells you that in some sense, the time must increase, maybe sometimes can increase faster than the inverse of the measure, but it cannot do the converse. You cannot find systems for which there is an invariant measure and the heating time is too short, generically or typically too short. And this is a quite elementary fact, and the proof is like a formalization and an application of the famous first Borel-Cantelli principle. This is a consequence of the classical Borel-Cantelli result. But you see, we have no equality here. We would like to see under which assumption we can have an equality. And before we said maybe the equality is there if the system is chaotic enough. And so the point behaves like random point. So random point sorted like the invariant, distributed like the invariant measure. And what is this chaotic enough assumption that we can suppose? Here we are led to consider the speed of decay of correlation of the system, and in particular the speed of decay of correlation of the system with respect to Lipschitz observation, which is kind of a large class. I mean, there are a lot of dynamical systems for which the decay of correlation rate is known with Lipschitz observable, because Lipschitz observable are quite regular, so they are good observables. And so we formalize this decay of correlation in this way, given to Lipschitz observables in our system. We say that we observe a decay of correlation that is super polynomial if the correlation integral decreases faster than a certain function going to zero, which is going to zero at a rate that is faster than any power law rate. And of course, there are two normalization factors depending on the regularity of the observable. And there are a lot of dynamical systems for which you can prove something like this, including uniformly hyperbolic system, some non-uniformly hyperbolic one, and we will see some example. For example, negative curvature geodesic flows under suitable assumption, and also Lorentz-like flows, and so on and so on. So this is the definition of super polynomial decay of correlation. It means that the decay of correlation will decrease faster than any power law. And the following statement tells us that this is a sufficient assumption to get the logarithm law. So the statement says that if a measure preserving map on a metric space, so you can talk about Lipschitz functions. If this measures preserving system has super polynomial decay of correlation with respect to Lipschitz observables, and then you choose a certain target point y, and then the local dimension at y of the invariant measure exists, then the upper and lower power law indicator of the heating time will converge to the local dimension of the invariant measure at the target point for almost every initial condition x naught. So sorry, here there can be a x naught is always the initial condition. Okay, y is the target point, and x naught is always the initial condition. I think it's the same in all the previous slides. I had a little bit of a doubt, but I think there is no ambiguity. But in any case, y is the target point, is the center of this family of shrinking balls, and x naught is the initial condition, and for mu almost initial condition, you have this behavior for the heating time. It will scale as the local dimension of the system. Before I said we consider small balls as target because this is the easiest meaningful case to consider. But of course, it's important also to consider other kind of targets, because, for example, in this geodesic problem, you want to arrive, maybe you want to arrive near to a certain point, but with any direction. So you will consider, you may be led to consider as target a small ball time all the possible direction, and to shrink the radius of the ball, but without shrinking the set of the possible direction in which you want to arrive to the near to the point. So this target set will become like cylinders instead of small instead of small balls. So it's natural to consider other kind of targets. Well, the situation is the same also for other kind of targets. The only thing that really matters is that the target are regular set. And so you can prove that if the target set are sublevels of Lipschitz functions, you can define something that looks like the local dimension of this shrinking family of targets. But okay, it looks formally like a local dimension, but what it is the power law behavior of the measure of this shrinking set. And you can prove the same theorem as before. If you have a fast decay of correlation, then the heating time, even in these targets which are not balls, behave as this kind of local dimension, which is the power law, the scaling rate of the measure of the target. And once you have this slightly more general result, you can apply this in many directions, also to flows and so on, things like this. Now, I'm not going to enter in the detail because there is no time, but with these, as a corollaries of these theorems, you can prove the logarithm law, that is this equivalence between scaling rate of the time and the scaling rate of the measure for the classical Lorentz system, and even generalization of the classical Lorentz system, in which you can also have some contracting situation, and for the geodesic flow in variable negative curvature instead of being constant curvature, and so on and so on. Recently, I was led to consider similar problems in a much more difficult framework, which is the framework of non-autonomous systems. And this is because stimulated by a discussion with Davide Faranda, which is a climatologist, is a theoretical physicist who works in models of the climate behavior and so on and so on. As you well know, an important problem is to understand how this very complicated system, which is the weather, the climate, and so on and so on, behaves as some parameter is changing in the system, like the concentration of the CO2. And so the people who works in this field, they are interested in non-autonomous systems, and non-autonomous system whose changing rate is quite slow in some sense. So you can think about a system which is changing slowly, and while the system changes, you make many iterates of your maps, but the maps change with the time. And so what happens is that one can prove a statement which is similar to the above stated theorems. And the statement is more or less like this. Now, I will simplify the statement because the actual assumptions are a bit complicated, but I want to state the idea. And the idea is that, okay, even in the case where the system is non-autonomous and you have the maps which are changing, if you're in a situation in which you can, every time that you consider a regular starting measure, and then you iterate the measure by the push forward of all these different maps. And when you iterate this measure, everything converges to a certain, let's say, final equilibrium state mu. Well, you have the same statement. So you have the logarithm law. So the 18 time goes like the measure, and so the scaling rate of the 18 time is the same as the scaling rate of the inverse of the measure of small target. So something similar also hold in the non-autonomous case, but here the stronger assumption is that you have a kind of convergence to equilibrium, which means is a kind of strong assumption that is like, for example, it will hold if this sequence of map, they converge to a certain map. So this is the case that is also called asymptotically autonomous. And so this is a general statement. What can be possible application? For example, you can consider, if you like fractals, you can consider families of solenoidal maps and apply in a non-autonomous way. So there is a kind of attractor which is changing in the time, but still you have this equivalence in some sense between time and the inverse of the measure. And a similar situation is the situation of mean field coupled system that I try to visualize here, in which you have many maps which are in every of they are copies of the same dynamical system with maybe different initial conditions, and they interact a little bit, and the state of a certain system will make a perturbation on the dynamics of all the other systems, and they interact in the main field, and then you can prove a logarithm law also in this very complicated situation. Now, I see that the time is going very fast, so I hope I will arrive to say something about when the logarithm law doesn't hold. So in the case in which the system is not chaotic enough, what can happen? The, is it possible that the time can really be very much bigger than the inverse of the measure of the target? And we will see that there are relations with arithmetical properties of the dynamical system. And so let's introduce something that in number theory is a famous concept, which is a measure for irrationality of irrational numbers. We will see, let's take a certain irrational number and suppose that we have this continued fraction expansion, and we have the partial quotients of the irrational number. Well, you can define the irrational type. So you call the irrational number is alpha, the irrational type of alpha that we denote with gamma of alpha is defined in this way. So if the quotient increase, these are the partial denominators. If the partial denominators increase very, very fast, maybe you have a big irrational type. And what can be proved, this is classical number theory, is that the irrational type is also related to this Diophantine approximation problem. And the larger is the irrational type, the easier is to approximate your irrational with rationals. And you can also prove that every irrational is of type greater or equal than 1, and almost all the irrational are of type 1, but there is quite a large set of irrational of type larger than 1. And this can be called well approximable by rationals. What can be proved in the context of dynamical systems and about the asymptotic behavior of heating time is the following thing. If you consider a rotation by an irrational alpha, and gamma of alpha is the type of the rotation angle, then for all the possible target points y, the two scaling rate indicators of dating time, so the upper and lower indicator, they can be different. And in particular, the upper indicator can be proved to be always equal to the irrational type of the angle, while the lower indicator is always 1. And this is true for, as usual, for almost each initial condition. So sorry, here we need to put a 0 here because this is the initial condition. So what this theorem tells us is the theorem tells us that for rotation and for rotations on the circle with a certain angle which is well approximable by rational in the sense that his type is bigger than 1, for certain radii, the is much bigger than the inverse of the dimension of the target because the scaling rate behaves like gamma. But still, in the same system, for the same target, there will be other r, small r, for which, again, so in some, you take a shrinking sequence of bolts. For some of these bolts, you may find a time that is much bigger than the inverse of the measure of the ball. But if you keep shrinking, you will still find some smaller bolts for which the time is comparable to the inverse of the measure. And this will go on and on. So after this, you will find another smaller ball for which the time is long, and other ball for which the time is the inverse of the measure, more or less, and so on and so on. So we see that in this very simple example, the irrational types give you an example for which the time can be bigger than the inverse of the measure. But very satisfying example because still there are targets for which the time is like the inverse of the measure of the system. And so for me, I was curious to find an example for which the time is always bigger than the inverse of the measure, no matter how the radius is. And I was curious to see if, of course, another problem, another weak point of this example is that this example considered as a counterexample to the general principle behind the logarithm law is that, okay, this is a rotation, is a system which is not even mixing, is not chaotic at all. So, of course, the points are not random points. Another motivation for me was, but can we find some system which is chaotic and still the time is much bigger than the inverse of the measure of the target? It's not so easy because even if you generalize the kind of systems that you want to consider in dimension 1, for example, you may be curious to consider interval exchanges, which are generalization of rotation that can be a little bit chaotic, they can be weakly mixing. For interval exchanges, you have the same situation. The lower it in time indicator is always 1. So you cannot find a counterexample in this family. And what happened is that you can find a counterexample with rotations, but you have to consider a higher dimension. And it is sufficient to go in dimension 2 and consider rotation in the two torus, but you have to choose very carefully the angles. And now I make a long history short, I make just an example. There are a famous, let's say, pairs of angles which are called Jacob's numbers and Jacob's pairs, which are made like this. You take well approximable irrational for which the partial denominator they satisfy this recurrent relation. This relation gives you very well approximable numbers, but still there are many irrationals that satisfy this relation. And if you consider this kind of Jacob's vectors, let's say, because they are couples of numbers, what happens is that, roughly speaking, if you have a lucky radius for one coordinate, so the time is comparable to the inverse of the measure, for the other coordinate, you will find an unlucky radius. So if you are going to hit a coordinate, you will not hit the second coordinate. So you cannot hit really the point on the torus. If you are near on one coordinate, you will not be near in the other coordinate. This is not simple to prove, but this is what happened. And so you can prove that for this kind of, let's say, Yokots angles, the heating time indicators, the power law behavior, they goes to infinite, while the local dimension of the natural measure that you consider in this system is 2. This is a torus, two-dimensional torus. So you have infinite and the dimension is 2. So you break completely the logarithm law. But still you are not satisfied because this is still a rotation, so it's not chaotic. And but still you can change a little bit your system and starting from this system produce a chaotic system. And there are two ways to do it. One is to consider a skew product for which this rotation is a factor, and you can make the skew product to be polynomially mixing, and this is shown in this work with Rousseau and Saussure. And so we have a polynomially mixing system for which the logarithm law doesn't hold because you have the heating time is much, much longer than the inverse of the measure of the time. And another way to produce a counterexample is to consider, instead of maps, you consider flows, and you take suitable reparameterization of the uh, translation flow, and you make it a mixing system. This is something that was studied by Fayad before, and with the Fayad construction, you can provide such a counterexample, which is a mixing system. This is C infinite, and there is no logarithm law at all for any radius of the targets. So I think my time is over or almost over. Uh, what I wanted to say was about the distribution of it in times, but probably there is no time. I was meaning to talk about some exponential distribution of it in time in dynamical system, in random dynamical system coming from uh, stochastic differential equations, but probably is not. It will take too much time, so I think I can stop here. And these are some references for what I talked about. And I thank you for the attention. And if there are questions, I will be happy to answer.
Thank you for the nice presentation. Any question to the speaker? Patrick, do you have any question? You are muted. Yes.
I do actually. I'm very interested in the irrationality and so on, but I'm gonna have to go back and look at those. So, I think it'll maybe if you have references on the I forgot what was it called, the gamma.
So sorry, I wanted to go back because I have a comment, something that I forgot to say, so I wanted to remember. But the two, so let me see. Uh, so one paper about the long heating time is this one, and the other paper is not cited here because there was no space, but
Okay.
is a paper published on ergodic theory and dynamical system with Jérôme Rousseau and Benoît Soussol in 2014. Maybe I have here somewhere because I tried to summarize different things. Let me search if I have the citation here. But it is Ergodic Theory and Dynamical Systems 2014.
Okay, that'll be enough. Yeah, I'll find that.
Yeah, it must be here around. Let me see if this is here. No, it's not here. Okay, sorry.
No worries. Yeah.
I forgot to write this. By the way, if you write me, I can send you the paper. Is no
We
problem.
appreciate it. Sounds good. Great. Yeah. Yeah.
I'll send you the PDF.
Perfect. Thanks. Very nice talk. Very nice mix of things.
you.
So
Thank you.
thank you.
Any
I
other?
wanted
Yes.
to make a small comment because I think is relevant. Of course, I didn't have time to go into the proofs, but I mentioned that the proof of this is just the application of the first part of the famous Borel-Cantelli lemma. And let me say that the proof of this, that requires the decay correlation is somewhat, it uses something which is like the second part of the Borel-Cantelli lemma. The classical Borel-Cantelli lemma, you have independence. Here you have decay correlation, but this is something that was studied by many people, and there are generalization of the Borel-Cantelli lemma with some kind of weaker assumption than independence. But in this case, we have quite a weak assumption because it's with Lipschitz observable. So we have to do something a little bit more. So just to say this, the proof of this more complicated result relies on a kind of generalization of this second Borel-Cantelli statement.
There is a question in the chat, by the way, or someone asking if they can put a question.
I don't know if I can see. I don't. Let me see because I minimized.
I could
the
read
Zoom.
it if there's someone
Yes,
who asks.
thank you.
Yeah.
Now let me see if I now I see the chat because I okay. Okay, I see. Systems which are semi-conjugated. I never thought about this, but probably the semi-conjugation gives you some result on some kind of target. I mean, probably the semi-conjugation will give you some. You have to change the targets, but maybe I don't know. I have to think about. This is something I never thought about.
Any other question?
So there is another question which is about spectral perturbative. So I can say two things about this spectral approach. The first thing is that spectral gaps gives you exponential decay of correlation in many situations. So system, if you can prove spectral gap, you are likely to prove also logarithm laws. But the question was referring also to perturbative arguments, and I did not say because I did not enter in the second part of the seminar, which was about distribution of it in time. One technique to prove exponential distribution of it in time, one famous technique, is by perturbative arguments, perturbative statement about the spectral picture of the transfer operator, and in particular, what happened to the spectral picture of the operator when you open a small hole in the system. The small hole will be the target, and the system, once you open the small hole, becomes a system which is open and it leaks measure. And so the maximal eigenvalue, which for closed system is 1, will move a little bit inside the unit circle. And this movement can be estimated. And with this, you can prove exponential distribution of it in time. This is a famous approach which is due to Keller and Liverani. And this is what is used indeed in the SD paper that I talked about in the last part of the seminar. Yes, there is a relation. My answer is yes, there is a relation.
Is there any more question?
Yes, I want to ask a question. Am I audible?
Yes.
Yes.
Oh, okay. So, Professor, you said that this, in case of chaotic enough systems, where you're saying that that particular thing, super polynomial decay, it can be proved that these indicators are equal to the local dimensions, right? So, can you say anything about the inverse problem in general? So if for a system this indicators are equal to the local dimension, how much? This question may be very stupid, but how much chaos is there? How much chaotic you need to? What is the
Okay.
minimum
This
amount
is
of chaos? Right.
so. This is an interesting question. Uh, we have done something in this direction, but for example, if you consider a rotation by an irrational which is of type 1, so is in an irrational which is badly approximable by rational, you will have that the rational type of this number is 1. So in this case, you have a rotation and you have the logarithm law. The limit, the scaling behavior of the 18 time will be the same as the local dimension, the same as the measure of the target. So this is an example that is not for which you have the logarithm law, but the system is not chaotic at all. On the other hand, in some sense, the opposite is true. You can prove, and this is done in the paper with Rousseau and Sossol that I talked about before. You can prove a relation between the speed of decay of correlation and the gap that you have between the 18 time behavior and the local dimension. In some sense, what you can prove, the philosophy is like this. If the 18 time is much bigger than the local dimension, the 18 time indicator is much bigger than the local dimension, then the speed of mixing must be below a certain speed that you can quantify in some sense. So you kind of have the converse, but you cannot do the opposite because there are systems for which you have the logarithm law, but the system is not chaotic at all.
Yes, understood. Thank you. Thank
To
you.
understand. Okay,
Yes.
again, if you sorry, I didn't. My reference was not ready, so if you write me, I can send you the paper. So you will see something. Maybe if you have a
Okay.
different idea, maybe is a good direction.
Okay. Thank you, Professor.
Thank you.
Is there any more question? So, if not, let us thank the speaker again. And so we'll see each other again next Friday. We have a talk by another professor. Thank you. Bye, everybody. Tatiana.
Bye. I don't know if I stopped sharing. Let me.
Yeah, no, that's all. That's fine. You can
Stop.
Yeah.
Okay, I stop.
Yeah, bye.
Okay,
So,
thank you. See you soon. Bye
yeah,
bye.
bye, everybody.